Archimedes Principle. Let's state this. Any body completely or partially submerged in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the body. In other words, the buoyant force is going to be equal to the weight of the fluid that would have occupied that space that is being vacated by this body. Well, as legend goes, Archimedes was presented a problem by the ruler. The ruler had just been given a crown, and it was a beautiful crown. And the ruler wanted to know if this crown was made out of gold or whether the person who had given it to them had kind of given them a cheap crown made out of tin or bronze or something like that. And so you could always weigh the crown, but you wouldn't know what its volume was because it's got all these facets to it. And unless you melt it down into some compact volume, you wouldn't really be able to determine what the density of the material was. And of course, if you melt it down into compact volume, then you're destroying the crown. So the ruler wanted to know if there was a way to determine what the density of this crown was, and hence determine whether it was actually made out of gold or not. So Archimedes is working on this problem, and he's thinking about it, and he happens to be taking a bath, thinking about this crown problem. And he notices while he's taking the bath that his arms are being buoyed up by the water. And he's thinking about this, and he realizes that if he pushes his arms into the water a little bit more, that buoyant force is a little bit more. In other words, the more water he displaces, the more force he feels on his arms. Based on this result, he came up with this Archimedes Principle, and he figured out a way where he could determine what the density of that crown was without destroying it, and hence determine whether it was made out of gold or not. He was so excited by solving this problem that he jumped out of the bath and he ran down the street exclaiming, "Eureka, Eureka," which means, "I have found it." And he was so excited, but he forgot in the interim to put his clothes on. So evidently science is more important than maybe self-esteem or what others think of you. The science is more important. Archimedes was pretty brilliant. He's well known for helping to ward off the invasions of the Romans. And one such invasion, he had the Greek soldiers shine their shields and make it so bright that they could reflect the sun and focus it on the sails of the Roman ships and set the sails afire. It became known, if you were the Romans and you were invading Greece, that if you saw an old gray-haired looking figure running along the shoreline and organizing things, that you were in trouble, because it was probably Archimedes coming up with some kind of way to defend your attack. Back to the problem at hand, Archimedes' Principle. Here's a wordy verification of this principle. Consider a cube of fluid or some kind of volume of fluid within the fluid itself. So you have this volume of fluid and it's surrounded by like fluid. And one thing you can notice about this piece of fluid is that it was in equilibrium. So even though it's got weight, there's going to be some weight associated with this fluid. There's a force of the surrounding fluid such that it is in equilibrium, and the net force on it would be zero. So even though it's got weight, there's some kind of buoyant force by the surrounding fluid that is equaling the weight of that cube of fluid. Okay, sounds good. But what would happen if there was some way where you could remove that cube of fluid from the fluid and replace it with some other object? Maybe a piece of metal, maybe a piece of steel, or iron, or wood, or styrofoam, or something, and you're just going to occupy the volume that the fluid was still in. Well, the surrounding fluid doesn't have a brain, so it doesn't know what's actually occupying that volume. It doesn't know whether it's fluid whether it's steel, whether it's wood, whatever, it's still going to apply the same buoyant force on that volume as it did before. It doesn't know better. And so it's going to still apply the same buoyant force equal to the weight of the fluid that would have been in that volume as before. Well, if your object were steel, it's heavier than the weight of the fluid, and hence it's going to have an apparent weight equal to its true weight minus this buoyant force. So it's still going to sink, but it's going to sink slower than it would than if you had it in air. And hence it's going to oppose a buoyant force equal to the weight of the fluid that would have occupied that volume. How about that? So the buoyant force acting on a cube of steel is the same as the buoyant force acting on a cube of fluid of the same dimensions. In fact, the buoyant force acting on any dimensions of the same size would be the same because it's equal to the weight of the fluid that would occupy that volume. This result applies for a submerged object of any shape, size, or density. Cool. So when Archimedes was resting his arms on the water, his arms were sinking into the water, displacing a certain amount of water, displacing a volume of water that would have a weight equal to the weight of his arms, and that's why his arms were floating. Here's a mathematical proof of the same idea. Consider a cube of fluid, and it's got a cross-sectional area A and a height h. The change in pressure between the top of that cube and the bottom of that cube is going to be equal to rho gh from the formula that we've used before. The pressure at the top plus rho gh equals the pressure at the bottom. So the change in pressure, bottom minus top, will equal rho gh. Hence, the buoyant force is going to be equal to this change in pressure times the area, the cross-sectional area of the object. Well, the change in pressure is rho gh times the area, so that buoyant force is going to be equal to rho g h times the area, but h is the height, area is the cross-sectional area. That cross-sectional area times the height will be the volume of that cube. So the buoyant force is equal to the density of the fluid times the volume displaced times g. Well, the density of the fluid times the volume there is equal to the mass of the water or fluid that would occupy that volume. So the buoyant force is equal to the mass of the water or fluid times g, or the weight of the fluid that would have occupied that volume. So the buoyant force is equal to the mass of the fluid, which is the density times the volume, times g. And that's our formula for the buoyant force, rho vg. Here's a woman reading the Jordanian Times, and she is sitting in the Dead Sea. The Dead Sea has a very high density because of a lot of salt in the water, and hence she doesn't have to displace that much water in order to equal her weight. The human body is very close to being the density of pure water, and so if you're sitting in water that's more dense, then you just have to displace a little bit of that water in order to equal your weight. And so the buoyant force is equal to her weight. She can sit up and read the paper. What causes an object to float? Well, the weight of the object would be equal to the buoyant force. So if the object is able to displace enough fluid, enough water, equal to its weight, then it will float. So the buoyant force will equal its weight. The buoyant force is equal to the density of the fluid times the volume of the fluid that's been displaced times g, and that would equal the weight of the object, which would be the density of the object, volume of the whole object, times g. Let's get rid of a g on both sides of this, and we would have that the ratio of the density of the object to the density of the fluid will equal the volume of the fluid displaced over the volume of the object. Or we could say the volume of the object that is submerged, because that's what's displacing the fluid, over the volume of the whole object. That would be one way to determine the density of a fluid. If just by placing an object and seeing how much of it submerges into the fluid. Well, let's try this out. How much of an iceberg is actually below the surface of the water? For this, we know that the density of pure water, by definition, is 1 gram per cubic centimeter, and the density of ice is 0.917 grams per cubic centimeter, just a little bit less dense. The ratio of the object to the ratio of the fluid is the volume submerged to the volume of the whole object. In this case, that would be 0.917 to 1, or 91.7%. So if you had an ice cube sitting in pure water, 91.7% of the ice cube would be below the surface of the water. Only 8.3% would be above the surface of the water. When it melted, it would simply take on the volume that was submerged, because the water would equal water, and the level of the water wouldn't change at all. So, if you're looking at an iceberg dead ahead, and you're navigating the Titanic, and you think, well, if I just turn to the starboard side, I can avoid the iceberg and maybe avoid damage. The problem is, you're only seeing 8.3% of that iceberg. The other 91.7% is below the surface of the water. And hence, even though you think you're avoiding the iceberg by what you see on top, the hull of your ship might hit the iceberg down below, because there's a lot of ice. 91.7% of that ice is what you can't see. And possibly that is what happened to the Titanic. Here's a mechanism to determine how much antifreeze you have in your radiator. These balls have different densities, and when they float, then it means the density of the ball is equal to the density of the fluid, and that would tell you what ratio you have of antifreeze to water. So that could help you determine whether you need to add more antifreeze or not to your solution. Steel is much denser than water. How then do ships of steel float? Well, there's two ways you could approach this idea. You could say, well, there's air inside the ship, and hence the density of the ship as a whole, steel and air, is less than the density of water, and hence it floats. Or you can think of it as the ship just needs to displace enough water such that the weight of the water it displaces is equal to the weight of the ship, and that's why it floats. Thinking on this second idea, the Titanic could float in only 1 cubic meter water if you were to build a lock that was the same shape as the ship. Say that 5 times fast. You have a ship that has the same shape as the lock, and so if we were to squeeze a thin layer of water all the way around, it could float in 1 cubic meter water. All you have to do is displace water such that there's a thin layer of water all the way around your ship, and you can float the ship. So the water that you're displacing that's equal to the weight of the ship doesn't actually have to exist. In other words, you don't actually have to have that water that you're displacing that's equal to the ship itself. You can just displace a volume and have water around you, and that still will make you able to float. Here's a problem. A frog in a hemispherical pod finds that he just floats without sinking into a sea of blue-green ooze having a density of 1.35 grams per cubic centimeter. If the pod has a radius of 6 centimeters and negligible mass, what is the mass of the frog? Well, this is a buoyant force problem. We have the mass and weight of the frog going downward, and we have the buoyant force pushing up. Now, the buoyant force is on the volume of the fluid displaced, so that would be the volume of this hemispherical pod. So the mass times g, or the weight of the frog, will equal the buoyant force, which is the density of the fluid, volume displaced, times g. we can get rid of a g on both sides. So the mass of the frog will equal the density of the fluid, of the water ooze in this case, times the volume of the pod. That's going to equal the density of the water times the volume of this hemispherical pod. Well, a sphere is 4/3 pi r cubed. A hemisphere will be half that. So we have a volume equal to 1/2 4/3 pi r cubed. This will equal 1.35 grams per cubic centimeters. And then we have 4/6 pi times 6 centimeters cubed. The centimeters cubed will cancel out. And our mass of our frog will be 611 grams. That's a simple buoyant force problem. Here are some conceptual questions. Lead has a greater density than iron, and both are denser than water. Is the buoyant force on a solid lead object greater than, less than, or equal to the buoyant force on a solid iron object of the same dimensions? Well, if they have the same dimensions, they're going to displace the same volume of fluid. So whatever has the same dimensions within the fluid is going to have the same buoyant force. The buoyant force is equal to the weight of the fluid that's being displaced. So if you have the same dimensions, same buoyant force. If I put a ping pong ball down into the water, it's going to experience a buoyant force equal to the weight of the water displaced, equal to the weight of the water that would have occupied that sphere. That force is much greater than the weight of the ping pong ball. Hence, that force is going to throw the ping pong ball outward, and that's why the ball will go up. Let's try another problem. A pound of styrofoam and a pound of lead have the same weight. If they are placed on an equal arm balance, will it balance? The answer to this is no. Because if they have the same weight, that will balance, but the buoyant force on each of these is going to be different. If you have styrofoam, it's displacing more volume within the fluid of air, because air is a fluid. And so there will be more buoyant force on the pound of styrofoam because it's got more volume than on the pound of lead. And that buoyant force will force the styrofoam up, and the lead will go down, and it will look like the lead weighs more than the styrofoam because of the difference in the buoyant forces. Here's a third conceptual problem. A person in a boat floating in a small pond throws an anchor overboard. Does the level of the pond rise, fall, or remain the same? This is a good question, a very, very nice question. I'm going to let you think about it, and I won't give you the answer until the end of this lecture. That way you can end the lecture early if you don't want to know the answer, if you want to think about it more. So we'll give you the answer at the end. I'll tell you right now, it's not necessarily a straightforward, easy answer. So if you think it remains the same, no, it's going to be different from that. Here's the Archimedes problem. A bargain hunter purchases a gold crown at a flea market. After she gets home, she hangs it from a scale and finds its weight to be 7.84 newtons. All right, she knows the weight of the crown. She then weighs the crown while it's immersed in water of density 1,000 kilograms per meter cubed, and now the scale reads 6.86 newtons. Based on that measurement, is the crown made of pure gold? So we already know the weight of the crown, 7.84 newtons, but when you immerse it in water, it seems to weigh less because the buoyant force is going to be acting on it. Now the mass of the crown is going to be equal to 7.84 newtons divided by 9.8, or 0.8 kilograms. Let's see, by immersing it, whether we can find the volume of the crown. If we immerse it, it's going to feel a buoyant force, and its true weight minus the buoyant force will be equal to the tension that she measures, or the new scale rating that she measures. So the new scale rating will equal the true weight minus the buoyant force. So the buoyant force will equal the true weight minus the tension measurement. That will be 7.84 newtons minus 6.86 newtons, or 0.98 newtons, is the buoyant force acting on the crown. But we know that that buoyant force should be equal to rho v g, the density of water times the volume of the crown times g, so we can get the volume of the crown. It is equal to the buoyant force divided by the density of water times g. This will be 0.98 newtons divided by 1,000 kilograms per meter cubed times 9.8. The volume of this crown is 10 to the minus 4 cubic meters. Hence, the density of the crown is 0.8 kilograms over 10 to the minus 4 cubic meters, 8 times 10 to the 3 kilograms per meter cubed. We can look this up in a density table of common metals, and you would find that 8 times 10 to the 3 kilograms per meter cubed is most likely the density of tin or some kind of alloy of bronze, because the density of gold is much higher. Gold is 19.6 times 10 to the 3 kilograms per meter cubed, more than twice as dense as this. Hence, it's not made out of gold, and it's not necessarily a good bargain. This is the problem that Archimedes solved with the king ruler problem. I'm not sure whether that crown was made out of gold or not. So we don't know whether the person who gave the crown to the king or the ruler saved their head or not. Here's another Archimedes problem. A light balloon is filled with 400 cubic meters of helium. At 0 degrees Celsius, what is the mass of the payload that the balloon can lift? We have to remember that air itself is a fluid. Assume the balloon has no mass except for the contained helium, so the weight of the balloon will be equal to the weight of the helium inside, while the buoyant force will be equal to the weight of the air that would have occupied that same volume. So the lift will be equal to the weight of the balloon, or the buoyant force minus the weight of the balloon. The weight of the balloon is equal to the density of helium times the volume of the balloon, 400 cubic meters, times g, and that is 702 newtons. The weight of the buoyant force is equal, or the buoyant force is equal to the weight of the air that would have occupied the same volume. That's the density of air, 1.29 kilograms per cubic meter, times 400 cubic meters, times 9.8, 5,057 newtons. So the difference between the two will be our lift. 5,057 newtons minus 701 newtons is 4,356 newtons. So this balloon would be able to lift something that had that weight. The mass of that would be equal to that force divided by 9.8, 444.5 kilograms. So this balloon would be able to lift 444.5 kilograms, which would be more than a person. So if a person were grabbing this balloon, it would go off flying. Now for the answer of that third conceptual question. If you don't want to learn the answer, stop the video now, because this is the end of the lecture. But if you do want to know the answer, then listen on. All right, so you're in the boat. You're in a small pond, and you have an anchor. If you have an anchor, that's part of the weight of the boat. And so in order to offset the weight of the anchor, you have to displace an extra amount of water equal to the weight of the anchor. Now, water is less dense than the anchor, so that displacement is going to be more volume than the volume of the anchor itself. Hence, the pond's going to be displaced a little bit higher at that point. But if you throw the anchor overboard, now when it's in the water, it's only going to displace the volume of the anchor itself. And hence that volume is less than the volume of the water it was displacing when it was part of the boat. Hence, the volume when it's in the volume displaced when it's in the water is going to be less than the volume displaced when it was in the boat. Hence, we had more displaced water when it was in the boat, less displaced water when it's in the water, so the level of the small pond is actually going to go down when you throw the anchor into the water. So that's the answer to that third conceptual question. And that is the end of this lecture on Archimedes'